All right, so let's jump into some polar calculus, calculus with polar equations. Now, before we do that, though, we're going to need to talk about polar coordinates. So what is a polar coordinate? Well, polar coordinates are a new way to graph from rectangular coordinate systems. So we define a new coordinate system where we have an angle theta and we have a radius r. So when we look at the ordered pairs, let's get this all on the screen here. When we look at the ordered pairs are going to be defined as a radius, a distance from a center, and an angle that we call theta. So an angle of rotation, a rotation from the ray that defines 0. So I grabbed an image of a polar graph. You don't actually need to have a polar graph if you're talking about plotting polar coordinates, but it does definitely help. So this is a polar graph where we're thinking in terms of like circular graphing with angles. So as an angle increases, it goes in a circle and we go counterclockwise, clockwise. Counterclockwise is when we have positive increasing angles. So when we graph a polar coordinate, we are graphing from a ray that we're defining as the angle 0 and a radius that is going to be a distance from an origin point. So this being the origin, this being a radius of 0 at this origin. So when we have a positive angle, we go this direction. So a positive theta goes this direction, and a positive radius would come out along a ray, some radius r. And we would plot a point here that would be r comma theta. So that's the general, just like the gist, just pulling it out, putting it in like a little image outside of my larger polar coordinate system that I put over here. But let's actually look at it with some particular ordered pairs, some particular polar coordinates. So what's kind of fun about this is it can give us some really cool graphs when we get into the graphing here in just a moment. But before we do that, let's just talk about plotting these points. So if I have, so again, this, and I know the image is a little bit distorted, but this is the angle theta equals 0 is this ray. Now, by the way, in a polar coordinate system, you can cycle through the angles more than one time, and you can go again counterclockwise or you could go clockwise. So again, these can create some pretty cool fun graphs. So graphing in a polar coordinate system, if you want to graph the point 5 pi over 4, what you're literally going to do here is you're going to think, okay, my radius is 5 and my displacement of the angle is pi over 4. So from theta equals 0, we're going to go to pi over 4. This is why it's nice to have this polar coordinate graph, because we can see that pi over 4 is right here. So we'll go to pi over 4. So here's pi over 4. So we're going to displace pi over 4, and then along that ray, we're going to go out a radius of 5. So we would go 1, 2, 3, 4, 1, 2, 3, 4, my eye lost it, 5. You know what let's do here? I'm going to change the scale on this, and I'm going to say let's let each of these dark blue lines be a radius, unit 1. So that'll be 3, 4, and 5. And by the way, that blue circle now is a radius 5 all the way around. So I was doing I was going with the smaller blue, the more teal blue here. So again, along the pi over 4, we're going to go 1, 2, 3, 4, 5, and we would be right here for point A. So point A would be right there in the polar coordinate system, 5 pi over 4. Now, what about if we wanted to go to B is, what do we do with a negative radius? So interestingly enough, a negative radius, we would go to the ray, and then it's going to be a reflection. So a negative radius is actually a reflection through the origin along the angle ray. So a negative radius is a reflection through the origin along the angle ray. So a negative radius actually takes us, we're going to go to 3 pi over 4, the angle ray 3 pi over 4, but then we're going to reflect along that ray. The negative radius will reflect us along that ray through the origin along actually to the 7 pi over 4 mark. So 3 pi over 4 would be right here. So here's 3 pi over 4. If we had a positive 5, we'd be out here at positive 5, but that's not where we're actually reflecting through. So we're going to be down here and reflect right through the origin. So keep going down along the ray. We will be at this point for point B. So here's negative 5, 3 pi over 4. Let's label this one too. A was 5 and pi over 4. All right, and what about if we had 5 and 9 pi over 4? Well, 9 pi over 4 takes me all the way around to 2 pi and then another pi over 4. So interestingly enough, this guy is going to be at the same point as A. We can get, it's in the rectangular coordinate system, an ordered pair has just one, one name, like 5, 7. There's no other way to name the ordered pair 5, 7. You can't get there with any other directions in the rectangular coordinate system. But in the polar coordinate system, because of its circular nature, we are back at the same point. So here we are, A. This point is also the point C, which is 5, 9 pi over 4. Because we've gone one cycle all the way around. And then D equals negative 5, and then we could even have a negative radius and a negative angle. The negative angle is going to take me in a counterclockwise direction. So counterclockwise direction, negative pi over 4. 7 pi over 4, by the way, is also equivalent to negative pi over 4. So if we go negative pi over 4, so we go this direction, negative pi over 4. But then we have a negative radius. So that's going to reflect me through the origin along that ray out to my radius of 5. And so this point right here would be D, which is negative pi over 4 and, negative 5. I put the angle first. Negative 5 and negative pi over 4. Okay, so that is how we plot points. That's a very brief overview of the polar coordinate system. But that is how we actually plot points in the polar coordinate system, and a brief overview about what is the polar coordinate system. Now, one last thing before I walk away from this is we can also overlay the rectangular coordinate system right on top of our polar coordinate system and come up with some relationships between the Cartesian coordinate system and the polar coordinate system. So if I overlay X and Y right on top of this point in the XY plane also has a name called XY, where X is the horizontal displacement from the origin and Y is the vertical displacement from the origin. And we can utilize this relationship and come up with, because this is obviously a right triangle, we can apply a trig, there's all kinds of relationships there that are built into this right triangle now that we have R as a radius, we have X and Y are the two legs of a right triangle, and theta is the angle. So that said, I'm not going to spend too much time on going back and forth because I want to work actually in the polar coordinate system. So there are ways that we can work back and forth and relationships that can be built, and I put them here. Here's that same exact image, just a digital image that I created before starting this video. But if we ever wanted to convert back and forth the relationships that come out of that right triangle when we overlay the rectangular coordinate system over the polar coordinate system, this gives us this point right here also has that ordered pair XY in the rectangular coordinate system, and that tells me that X is equal to R cosine of theta, Y is equal to R sine of theta. Those two things we will actually be utilizing. We also have the relationship through Pythagorean theorem that x squared plus y squared is r squared, and theta equals the inverse tangent of y over x. And so if we ever wanted to go back and forth between rectangular coordinates and polar coordinates, we could utilize those. What I want to focus more on in this intro to our polar calculus is how do we actually graph polar curves? So if we come across a polar curve, so graphing polar curves, here's an example. This is what we're going to do. Graph the following polar curves. Our first one being r equals 1 plus the sine of theta. So how do we do that? And I just want to go through a couple quick strategies for doing that. So graphing polar curves. So graphing a polar curve or a polar function. So we're gonna be working with polar functions where we have r is going to be defined as f of theta. So just some quick strategies for doing this. One, we can plot points. So we can come up with a t-chart, plot points from a theta versus r t-chart. Right? So I'll show you that with that example. So we can pick some values for theta and pick some, find the corresponding values for r, and we can plot those. Okay? That's definitely one way to do it. For me, a little bit faster way, and certainly if you're pretty good at graphing trig functions, another way that you can do it is you can actually graph the theta versus r graph and use that to guide the polar graph. This is, in a lot of ways, just a faster way to plot points. Faster, or maybe not even faster, but a more visual way to plot points. Okay? So what I mean is we are literally going to take and we're going to graph something. I'm just going to draw a sine curve here. We're going to graph and use this graph to go into the polar coordinate system. Okay, so we can plot points, we can graph, and our final way is we can use what are called families of curves. I guess there's actually a fourth way, families of curves, to find the pattern or graph, okay, of our polar curve. We do start to rely on this a little bit more. There's definite patterns, and we'll see things like what are called cardioids, or we'll see flowers that have a certain number of petals based on how the equation is set up. So on these families of curves, I would also say this is another place where we could, I was going to say there was a fourth method, but I'm going to add it into this. You could also use technology. Obviously, you can use graphing calculators, and Desmos has quick ways to graph polar curves. Okay, so let's go through just a couple quick examples of graphing some polar functions, doing it by hand, show you real quick how to do it in Desmos, and also talk very quickly about those families of curves that we can utilize. Okay, so let's start here. If we wanted to graph r equals 1 plus the sine of theta, and we want to graph that polar curve, what does that look like? How does that get traced out in the polar coordinate system? And so what we could do here is we could plot points, or we could graph the theta versus r curve. So I'm going to go with that first. I'm a very visual person, so I'm going to go with that first. I'm going to say, okay, so I know what the sine curve looks like. What does the 1 do? It shifts it up. So here's theta. Let's let this, I'm going to let that actually be 1, not be 2. This is actually the r-axis now. And I'm going to graph this, so I'm going to say, I'm going to call this 2 pi. That 1 is a vertical shift of the sine curve, so it's going to shift my sine curve up 1. So I'm just kind of going to give myself that baseline here from the shift. That's going to shift my sine curve up 1. It's going to start here at 1 at pi over 2, pi 3 pi over 2. This is 0. At 1 we start here. At pi over 2 we would be up at 2. At pi back down to 1. 3 pi over 2 we're going to be down at 0. And by 2 pi back to 1. So we're going to have a curve that looks like that. Okay? Okay, we could also have done that if you prefer plotting points. If you like plotting points and plotting points works for you, this is a graphical approach. We could also have done a quick little t-chart here, and we could have said, okay, so let's do just the the theta versus r. And we could just fill in the same same kind of key points, pull the same key points off of the graph, and at 0 plugging in. So if you like just, you kind of like this more tabular table form, go for it. I mean, I don't really care how you graph your polar curves. I'm just going to show you, I'm going to give you a couple tools, show you a couple ways to do it. So if you prefer these tables, go for the tables. And I do find some students have learned this way and like using the tables. So if we plug in 0, 1, pi over 2, we're going to be 2, 1, 0, and 1. Okay, so we could do the same sort of thing there too. These are now ordered pairs that we could plot in the polar coordinate system. We can also use the graph. Again, I think of the graph as like a visual way to plot points. And so I'm going to come over here. This is my polar coordinate system. I'm going to go ahead. I'm going to set my radiuses. This is actually going to be 1/2. I'm going to call this 1, and I'm going to call this 2 in this graph. I'm going to zoom in here so we can see it just even a little bit more. There we go. Oh, no, I think that's all. I think that's gone off my screen, so I can't zoom in quite that much. Maybe right about there. Okay, okay. And so let's graph this. Let's actually change those to black, and then I'll do my curve in red so it'll really stand out. Okay. Okay, so we start off at an angle of 0. So remember, this point right here corresponds to the ordered pair 1, 0. And this corresponds to the ordered pair pi over 2. I always want to put the angle first because I always think in terms of the angle first, but r and then pi over 2 and so forth. So what I see right here is as the angle increases, so I'm really thinking about, like, if you could see my head, I'm kind of thinking about rotating around this as the angle increases. So in a clockwise manner, I'm thinking of rotating around this circular coordinate system, and I'm thinking about what's happening to my radius. How is my radius fluctuating? Is it going up, down? What's happening here? So I'm literally starting at 1. So I can plot right here at 0, at the angle 0, I'm starting at 1. And then I notice that my radius literally like increases, like spins outward, increases as we go. It ends up, by the time I get to pi over 2, I'm up here at 2. And so what has happened here is I have increased my radius through all of those angles until I get to 2. So I would have a curve that looks something like that. And then, by the way, that 2, right, that circle for 2 comes all the way around. Let's trace it all the way back here, and this is 2 here, and my 1 was right here. Nope, I lost it. I went too far up on the 2 there. There we go. There's 2 all the way around, and 1. Okay, and let's put 1 here as well. And then we notice that then the radius, then on the next little segment, so going up there, the radius increased, but then on the next little segment, the radius decreases back down to 1. So then the radius decreases, and there's symmetry, right? There's definitely some symmetry here in that sine curve. So we've got that curve going up, hitting 2, coming back down, hitting 1, and then the radius decreases all the way down to 0. Okay, by the time we get to 3 pi over 2. Well, what would that look like? Well, through this entire region, it gets smaller, 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 till it comes in and it hits 0 right there. And then on the next little segment, from 3 pi over 2 to 2 pi, that radius increases back up again to 1. And if we were to continue the cycle, we would continue going up and down. This is actually what's called, it's a heart, right? That has that heart shape. So notice we have the heart shape here. That is what we actually call a cardioid. That's in a heart shape is a cardioid graph in polar coordinates. Okay? And that's absolutely what we have right there. So we have a cardioid happening here. Okay, we would have gotten the same thing. I plotted the points down here. If we had done the points as well, we would have gotten the same thing. We can see those points actually. We did actually plot those points as we went around here. Okay. Okay. All right, so let's keep this rolling. Let's look at the next curve here, and then we'll talk about families of curves. By the way, cardioid is one of the families of curves, and we can recognize it based on this particular pattern, that this is like an A plus B sine of theta, and then it has to do with how A and B are related, and in this case A actually equals B, which is generating that cardioid. So I'll show you guys a little table with some families of curves here in a second. Okay, but before we do that, let's look at one other curve that will give us another family of curves. And so let's look at this guy. So what happens if we change the period? What if we have a trig function but the period changes? So notice here we've got that 2 theta, so the period here is going to cycle through every pi. Okay, so what does that look like? Well, let's graph. I'm actually not going to create the t-chart on this particular one. On this one, I'm just going to go with, and if you like those t-charts and you prefer just writing out values, then go for it. Okay, that's your method. However you want to graph these polar curves, you pick. This should be review. You should have graphed polar curves at length in a pre-calculus course. So let's say this is, I gotta call that 2 pi and that pi and this pi over 2, and this 3 pi over 2, and I don't know that I'll put all these in, but let's go pi over 4 and maybe just the first 2, 3 pi over 4. Okay, so we also have an amplitude, by the way, of the 3, so that's why I adjusted for the 3. We got 3 sine of theta. It's going to cycle through, and we're going to start at 0, then we're going to be up at 3, and then back to 0, and then down to -3, and back to pi. So we're going to have something that looks like this. Twist this and get a nice curve. Let's zoom in there a little so I don't get, my pen doesn't get shaky. And back up, and then back up here, back down, and back up again. Okay, so what is that going to do? So let's think about it. So let's zoom, look at our polar curves again. So check out what's happening here. By the way, we've got some negative radiuses happening here, so we'll have to think about those reflections. So what's going to happen here when I go to graph this, let's say this, I'm going to make this graph just a little bit bigger if I can. Okay, so let's call this, oh sure, let's make this really big. So let's call this 1, and call this 2, and call this 3. Okay, so I'm labeling, and make sure you do that, right? Like label, just like you would do in the coordinate plane, label where your radiuses are. So by the way, that means that circle, right? This is going to be 2 here, and this is going to be 3, and this is 1 all the way around, and this is 1, and this guy's 2, and this guy's 3. 1, 2, and 3 all the way around. Okay, so let's do this in red so it'll really stand out. So notice that we start at 0, and by the time we get to pi over 4, we're up here at 3. So the radius is, this was the theta curve, and this is r. This axis is the r-axis. So notice that the radius starts at 0 when the angle is 0, and then as our angle increases up to pi over 4, our radius increases all the way up to 3. And so when we think about what that's going to look at, by the time we get to pi over 4, by the way, pi over 4 is right here. So by the time we get to pi over 4, we're out here, and we start here at 0. And through that entire range, as that angle increases, so as the angle is opening in a counterclockwise manner, this is going to spin out and up, right? Our radius upwards, our radius is increasing incrementally as we go up in the angles till we get to that pi over 4. And then it hits that point, and then on the way back down, as the angle, it continues to increase towards pi over 2, the radius goes back down to 0. So then, and that's symmetric as well, so it's going to spin back down. So by the time we get over here to pi over 2, and you just think about like at each of these little points, that radius is going down, 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 down until it gets to right there. Okay? And we're creating that, what's actually called a leaf or a petal. Okay, so we've created a little petal here. Now what's going to happen? Well, as we continue to increase from pi over 2, as we're going from, essentially as we're in this quadrant from pi over 2 to pi, notice that the radius is actually negative, right? So when we get here to 3 pi over 4, we actually have a negative radius of 3, right? This point right here would correspond to the r theta point of -3 pi over 4. Okay? But a negative radius is a reflection. So since a negative radius is a reflection, at 3 pi over 4, we're actually going to be right here, this point. So all of these points that are in here, as we go to plot all the points that would normally be in this segment, in this quadrant essentially, they're going to be reflected and they're going to be plotted over here because they all have negative radiuses. So we're going to, if you think about it, if we were positive and we were going out to 3, we'd have a loop that would look like that, but that's not what happens. What happens instead is those points get reflected down here, and too much touching on my screen, and we go this direction, and the radius and the petal, and then on the opposite side of 3 pi over 4, we go back down. So the petal traces out this direction and then back down to 0 on the radius. Okay? And we get a petal that looks like that. And then we continue, and now we're in this quadrant from pi to 3 pi over 2, and we're positive again. And so at this point, by the time we get to 5 pi over 4, we're back out at 3, and we've gotten half of another petal, and then we come back to 0. And then again in this region, so we just did that up and back down, and then in this region, again, we would be, so now we're moving into these angles from 3 pi over 2 to 2 pi, but again, we have a negative radius, so that reflects us all the way back into this area, okay? So we're going to take our curves, and we're going to have, so as we continue here, we're going to end up tracing out and coming back down, okay? And notice what we end up with. We actually end up with these petals, 4 different petals. We end up with 4 petals of a flower. A rose, actually. So again, that's going to be a family. That is a family of curves as well. Okay? And so we're going to talk about a family of curves when we have something of the form sine, we should say a sine or cosine, actually, of n theta. Okay? So we end up with a family of curves that we can recognize will create petals. Okay, speaking of those families, let me show you a quick little image where we have all of the families. Because, we could spend loads of time. We could spend weeks on graphing polar curves and how you can get just some really cool, amazing graphs with polar curves. Beautiful graphs, actually, with polar curves. But I want to jump into the calculus. So in our next video, we'll do just the calculus. But in order to do the calculus, we got to know how to graph these. So let's take a look at some families of curves. So some families of curves, you can find these families of curves in the textbook. You can find these families of curves just on the internet. Look up families of polar curves. But here's just a list of some. So if you I'll just leave this on the screen here. And so this is just a way that you can get families of curves. The two that we looked at I think we had a cardioid, and we had our n was actually even. So we had a rose curve where n was even, and that's why we had n happened to be 2 in the example we just looked at. But we had 4 petals. So when n is even, you end up with 2 n petals. When n is odd, you end up with just n petals. So kind of interesting, some fun patterns that arise when you look at polar curves. We had the cardioid. So we had a cardioid, and it was oriented a different direction than the one we have here. It was an upside down heart, the one that we graphed, but we had something like this. And then you can get into even these limicons, where you've got these inner loops and that kind of stuff. And anyway, I love polar graphs. Polar graphs are really fun. One last quick thing. Let me just jump to Desmos on my screen here and show you guys how to graph in Desmos. This will be really quick. So to graph in Desmos, what you're going to do is you're actually going to type in the actual polar curve, and then I'll show you how you can even change the coordinate system. So what did we have? We had r equals 1 plus the sign of theta. I literally just typed the word theta, Theta, and that's what creates the theta curve. Notice it immediately gave me that cardioid. It automatically assumed I wanted it from 0 to 2 pi, one full period. You can always adjust that. It gives it to you there. The other thing that you can do, let me make this smaller so it's all on the screen. The other thing that you can do is kind of distorted it when I did that. There we go. The other thing that you can do is you can change the settings, and you can use that in the wrench right here, and check it out. You can do polar curve or polar grid, and you can get your polar grid like that. Okay. All right, guys, I'm going to end this video. Hopefully this was a review of graphing of polar coordinates and graphing polar curves, but definitely, if not, check out those families of polar curves and do some practice just graphing of polar curves.